In this video I want to talk about a new concept, and that's the concept of an absolute value of an average value of a function. So we have here a function f defined on some interval a b with its values all real numbers, and we ask the question, well, what is the average value of f, this function, on this interval a b? So firstly, what do we mean by an average value? So when we have a finite number of quantities, right, say the number of goals scored by a soccer team in every match of the season, then we can calculate the average of those quantities. Right. But here we don't have a finite number of values of f. Right? We have infinitely many values of f. So we have to make a different plan. Now what we're going to do is, we're going to, instead of finding straight away an average value, we're going to start off trying to find an approximation for what we think should be an average value for the function f, and then see what happens if we make that approximation better and better. And so how we do that is as follows. Right? We're going to basically take a sample of points from A, B, and then calculate the average value for f at those points. Right? And we pick this sample of points in a particular way. Right? So we start off, we say, let delta x be b minus a over n, right? And then we let x1 be a plus delta x, and in general xk plus 1 will be xk plus delta x. Right, so we're going to start off by picking a point x1, and with this length of this interval being delta x, and we're going to have a point x2, and so on. In general, we'll have a point xk, next one xk plus 1, and so we carry on, right, until we get to xn, and that will be b. Right. So we pick these points, a sample of points, x1, x2, x3, and so on, up to the last one, which will give us xn. Right. And what we do now is we calculate the average value of f at these points, only at those points. Right. So let's run at that as average n, so AB with a subscript n. Right, so that would be the average value for f at all of these points we've picked. Right, so that would be, right, so we're going to add the values for f at all these points. And now the average would be all these values added together divided by the number of points n. Right. So you can write that 1 over n, sum I from 1 to n, f of xi. And now just a little algebraic manipulation shows that we can write this as 1 over b minus a, sum I from 1 to n, f of xi delta x, where delta x is b minus a over n. Right, so delta x is the length of each of these small intervals. Right. So what do we have there? Well, if we think of it geometrically, right, each term in that sum is going to give us an area. The first term, right, we have f1, which is that height, or f of x1, times delta x, which is that length. Right. So the first term in that sum gives us that area. Right. And in general, right, say the k plus 1th term will give us that area. Right. And we are adding together all these areas. Right. Now this should look very familiar to you. What we in fact have here, right, is 1 over b minus a, and this sum, right, is a Riemann sum for this function f. Right. And now what happens to a Riemann sum as the number of intervals, right, or then n here, becomes large? Well, as n goes to infinity, this Riemann sum will go to the definite integral of f over the interval. And of course we're multiplying by 1 over b minus a. Right, so this is f. F is integrable. Right. So, remember, this quantity, AVN, is supposed to be an approximation for the average value of f. Right, so the average value is approximately equal to this AVN, and this AVN, as n goes to infinity, goes to 1 over a minus 1 over b minus a times the integral from a to b of f of x dx. Yeah. So now we can well imagine that the more points we take in our sample, in other words the bigger n gets here, the better an approximation this AVN will be for the actual average value of the function f. Right. So we can say as n goes to infinity, the average value, n, this approximation, goes to the actual average. Right. So if AVN, as n becomes large, approximates the average value of f, and it tends to this quantity, right, then it seems reasonable for us to conclude that the average value of f is actually given by that quantity. Okay. And that's our definition for average value. We write it as f put note AVE, and we define it to be 1 over b minus a integral a to b f of x dx. Okay. So it's important to note that what we've done here is by no means a mathematical proof. Okay. It's a convincing motivation for why this definition is appropriate. Okay. So in the next video we'll look at an important theorem relating to average values.